Welcome to PowerUp, a podcast show hosted by Maurizio Di Paolo Emilio that brings life to some of the stories on power electronics technologies and products featured on PowerElectronicsNews.com and through other AspenCore media publications. In this show, you'll hear both engineers and executives discuss news, challenges and opportunities for power electronics in markets such as automotive, industrial and consumer. Here is your host, Editor-in-Chief of PowerElectronicsNews.com and eeweb.com, Maurizio Di Paolo Emilio.
Hello everyone and welcome to this new episode of PowerUp. Today we will talk about innovations in generative AI power delivery. And our guest is Maury Wood, Vice President of Strategic Marketing at Vicor. He held senior roles at optical fiber test and semiconductor companies, including NXP, Analog Devices, and more. Our guest will delve into the cutting-edge solutions that are helping mitigate the enormous energy demands of generative AI, GenAI. From understanding why GenAI is so power-hungry to exploring innovative power architectures, this episode will illuminate the path towards more efficient, sustainable AI computing. So let's talk with Maury. Hi, Maury. Thanks a lot for being here. How is it going?
Good. Thanks, Maurizio. Nice to be here with you today.
So where are you located, Maury?
I'm in Andover, Massachusetts, in the United States.
Good. So today we will talk about GenAI, innovations in GenAI power delivery. But before that, I have a couple of questions to share with you. So please introduce yourself. Tell us more about you, your background.
Sure. Yeah. I am the Vice President of Strategic Marketing here at Vicor. I have spent the majority of my career in the semiconductor industry. I was at Analog Devices. I was at NXP, at Broadcom, spent some time in the fiber optic test industry, and then I joined Vicor just about 2 years ago.
Great. So Gen AI, before that, so what's artificial intelligence? What's AI for everyone?
Yeah, I think 25 years ago, there were some advances in machine learning, and those sort of continued with a sort of almost a predictable level of innovation. And then, of course, I guess about 2 years ago, right now, OpenAI and other companies released to the world large language models that had the ability to generate content, hence the sort of the concept of generative AI. And I think everybody's aware of the impact that has potentially on productivity, personal productivity, and industrial commercial productivity. So it's a whole new world. But they, of course, this technology has some very, very demanding power requirements, which I think we're here to discuss, Maurizio.
Yes. Let's talk about. So, may you explain why Gen AI training processors are so power intensive compared to other types of computing?
A fundamental reason is because the processors used for doing Gen AI training are characterized architecturally by just massive levels of parallel operation execution units in those processors. So you have literally thousands and thousands of floating point multiply accumulate units that can do other math operations. And it is the demands of that parallelism, and then the tightly coupled memories that are now being implemented in chiplets next to these processors that drive the current levels at low voltage. And so the other sort of the corresponding trend, of course, is that as wafer fabrication becomes more and more advanced with extreme ultraviolet lithography, for example, the operating voltage of the transistors that comprise these processors drop, and with the massive parallelism that I just noted, the amount of current you have to deliver at those low voltages has just skyrocketed to levels that I think I can really safely say that nobody anticipated. I think that the growth in that current delivery, just measured in amperes, is higher than I think people really ever expected to see possible in this class of, it's just sort of it's sort of exploded geometrically from what we saw even just four or 5 years ago.
So what makes so challenging, related to manage the electric current demands of high performance computing, especially GenAI? What makes so challenging?
There's a number of dimensions there. The operating voltage, which might be, say, 0.7 of a volt, has to be regulated to a degree to which there's no potential damage to the processors, because, of course, as I'm sure you're aware, they're very expensive. Nobody wants to have reliability issues. So the limits of the regulation itself are very constrained. So you're at the top level, you're required to deliver a massive amount of current with a very, very good regulation. And so the control that's required to, essentially the control theory, the implementation of the control loop and how you equalize or compensate that loop is very challenging. That's one element. As I said, sort of just the level of current. So what you are up against very, very rapidly is a realization that on the small accelerator printed circuit boards that these processors are mounted, there's a limited amount of real estate, if I can call it that, area on the printed circuit board that is available for the power delivery subsystem. And so you have to somehow develop a power supply which can fit in that constrained area while maintaining the tight regulation, while delivering thousands of amps of current. And then the third major element is that these processors, if you look over time at their demands for current, and it's sort of depending on what the algorithms are doing at any given moment, measured in microseconds, the transient demands for current are extremely dynamic. And so not only do you have to maintain the tight regulation with massive amounts of current, but you have to do that and be able to respond rapidly to very large changes in the delivery of that current. So this in practice could be also sort of limitation of traditional power supply architecture, if we would explain. So if we would explain how have traditional 12 volt DC and even nearly 48 volt DC power supply architecture fallen short in meeting the needs of Gen AI processors. So we are talking about transient and current, as you mentioned, in practice. Absolutely. And sort of a related issue there with anybody with experience with power supplies would understand, sort of given those constraints, comes even at high levels of efficiency, you're still going to have a lot of heat to be able to that you must deal with in order to make sure that your power supply remains reliable over time. And so you sort of have a very tight box of limited area to work with, the need for just ridiculous, frankly, amounts of current, very high and very challenging dynamic transient operating conditions, and then you have to be able to pull the heat away in a way that is again allows for the long-term reliability of both the processor and the power supply itself. So let's talk about innovations from Vicor, innovations in power delivery. So could you elaborate, explain on the advancements Vicor has made in power delivery, particularly with the vertical power delivery solutions and factorized power architecture? Right. Yeah, the factorized power architecture is sort of fundamental to our approach to powering Gen AI processors. So the concept is similar to sort of the established, if I can say, approach of using an intermediate bus voltage, and then at the point of load doing regulation from that intermediate voltage, which has evolved. In this world of training processors, both through efforts to standardize and because of how, and we can talk more about the merits of 48 volts, but 54 to 48 volts has sort of emerged as the voltage that you're going to be dealing with coming onto the accelerator module that is the printed circuit board assembly that includes the processor and the point of load power delivery network and components in the power delivery architecture, if you will. So again, the intermediate voltage has kind of evolved over time, sort of the more traditional, not the way that we've done it, but has been typically a 4-to-1 ratiometric conversion from 48, let's say, to 12 volts. And then you would distribute that some distance on the printed circuit board to the point of load voltage regulators, which are implemented using different architectures and topologies. In our approach, without getting into the details at all, we have a regulation stage, but the ratiometric transformation of the voltage occurs at the point of load as opposed to in the bus converter stage. And and maybe you'll have some follow-up questions, Maurizio, I imagine you will, but because of the amount of current delivery that's required, any length of printed circuit board copper trace represents essentially a resistor, even when they're measured in microohms. And of course, you're going to have efficiency issues related to the power supply components, the power delivery components, but you're also going to have the dissipation in the printed circuit board itself. And of course, as you increase voltage,
thermal management.
Sure. Yeah, exactly. And of course, as I'm sort of going to assume that everybody that would listen to this and have an interest in this understand that the higher the voltage, in order to deliver the same amount of power, the higher the voltage, the lower the current that you're going to have to deal with. And by maintaining a higher voltage to the point of load, and then doing the ratiometric transformation, which we refer to as sort of the VTM stage, or the voltage transformation stage, or the current multiplication, it's sort of the same concept. If you can keep that closer to the processor, then you limit the amount of power dissipation in the printed circuit board itself, which is an obvious merit. Everybody at all levels of the supply chain, for data centers, for AI data centers, for GenAI generally, are looking for the highest efficiency utilization of the energy that's delivered to that facility. So all of these things add up. And of course, with the tens of thousands of these GPU-based processors for GenAI training, it rapidly sort of multiplies out to being a big number that's significant, particularly given the fact that once these data centers kind of, the power is applied to these server racks with these accelerators, it's never turned off. I mean, it's 24/7 continuous operation, and there's a lot of pressure. I'm sure you're aware. I think everybody's aware, and concern around Gen AI power consumption, energy consumption, and making sure that there's the highest efficiency possible.
So you are talking about data centers. So any other application, may do some other examples to understand the practical application of your solutions.
Well, we serve a pretty broad set of market segments. I'm trying to think in the context of this. I guess I'd push back a little bit and say that we don't see at this point, for example, with traditional, x86 server processors for data centers, yes, sort of the more historical market, the power levels are rising, but they're not rising as fast as these training processors for AI are rising. So they're kind of now in the 400 to 500 watts TDP domain, whereas for the next generation AI, you're talking about 2,000 watts and higher. So given the fact that you're operating at 0.7 volts for the main rails there, you can see that the continuous current delivery is thousands of amps. And so we're not really seeing that elsewhere. We're expecting that things like autonomous vehicles will integrate, pretty powerful processors for the purposes of safe autonomous driving. That's just emerging. But I think that would be the other area besides something like edge computing, where it's possible you might have enough inferencing going on that you're going to start to drive to higher and higher power levels. But from a standalone single accelerator, GenAI is kind of off on its own in terms of that power delivery.
So the last one for this episode of PowerUp. So talking about the future of power delivery networks. So what do you see as the future in supporting even more demanding AI applications? So where do you see, in data center, as you mentioned, the next challenges, which is how do you foresee, and how is Vicor preparing for this next future?
Yeah, that's a great question, Maurizio. And I think the most important trend that we haven't discussed right now is that there are, as I mentioned earlier, there's a limited amount of printed circuit board area in which to position, topologically position the point of load converters, any bus converters that you have. Mm-hmm. The sort of the first generation systems, if you were to look, those voltage regulators are placed what's become known as laterally around the chiplet based package that includes both the high bandwidth memory and the GPU based processors themselves. The trend that I think is the most key trend to your question is the migration to those to a vertical positioning, typically beneath the processor, which has both electrical and thermal merits. So it's possible to construct, and it's very complex, sort of a thermal mechanical stack. And in most cases, we're seeing now finally the wide embrace in the industry of liquid cooling. And so you can imagine sort of at the top is a cold plate that's liquid cooled. And then eventually, as you sort of traverse that stack mechanically through the thermal interface materials and whatnot, below you're going to have the point of load converters with an extremely short, measured in millimeters, 1 or 2 millimeters, with respect to the amount of copper that has to be traversed before you're actually at the microballs of the package. And so that's a further way to not only reduce any dissipation in the printed circuit board, which of course kills efficiency overall, but also allows us to address some of the things we talked about earlier, which is it improves transient response, it improves regulation, it improves, it creates more space for decoupling, which is a critical sort of where do the decoupling capacitors go when you're so space constrained? So all those sort of challenges can be better addressed when you adopt this vertical power delivery, the VPD solution for GenAI processors. So that's a very key trend here, along with the liquid cooling.
So thank you, Maury. Thanks a lot for joining us at PowerUp. Thank you.
My pleasure, Maurizio. Thanks so much.
That brings us to the end of this episode. Stay tuned with more news and technical aspects about power electronics. If you are listening to this on the podcast page at eetimes.com or powerelectronicsnews.com, links to articles on topics we have discussed are shown on this page. PowerUp is brought to you by Aspen Core Media. The host is Maurizio Di Paolo Emilio, and the producer is James Eade.